Good morning, my name is Sam and I'm here at the TCC Learning Commons. I'm doing a workshop for Chemistry 1045 on thermochemistry. Does anyone have any questions?
It says a 71.3 gram piece of metal at 88 degrees Celsius is placed in 129 grams of water at 23 Celsius contained in a calorimeter. The metal and water come to the same temperature at 26.7 Celsius. How much heat did the metal give up in the water?
Okay, so it sounds like the general equation for this chapter is Q equals mc delta T. And this question just sounds like we have a Q of metal and we have a Q of water, and we're going to set them equal to each other. So I would say Q of metal equals Q of water. And then now I'm just going to reread all the numbers. So the metal weighs 71.3 grams, which means we're going to have mc delta T of metal equals mc delta T of water. So since we know the mass of the metal is 71.3 grams, we're just going to plug that in on the metal side. One important thing to know before we keep going is whichever side is hot is going to have a negative. I believe the metal is the hotter one in this case. Turned off. Okay, yeah, so the metal's starting at 88 degrees Celsius, the water starting at 23 degrees Celsius, which means whenever we have delta T for the metal, we know that delta T is T final minus T initial. If something's cooling down, that means the initial temperature is higher than the final temperature, which means you're going to have a negative number. So that's why the hotter side has a negative on the outside. So we know the mass of the metal. We know, do they give us the specific heat? The metal and the water come to the same temperature. Oh, they want us to find the specific heat. Okay. So we don't know the specific heat of the metal, so I'm just going to put C for that. And then for delta T, we know that the initial temperature was 88 degrees Celsius, correct? Yeah, 88 degrees Celsius. So since delta T is final minus initial, we're going to put the 88 here because it was the initial temperature. And then the final temperature is just whatever temperature they came to. So it looks like they come to 26.7 degrees Celsius. 26.7. Okay, so that's the left side of the equation. Now we just have to do the same thing for water. So the mass of the water is 129 grams. The initial temperature was 23 Celsius. So 129 grams. 29 grams, yeah. Specific heat of water we know is 4.184 joules per gram degrees Celsius, or Kelvin, either one works. And then the final temperature is going to be the same because, whenever you put a hot object and a cold object in contact with one another, they have to reach the same temperature. So the final temperature is still going to be 26.7, but it's the initial temperature that is different. So it's 23.0 degrees Celsius. So it looks like we have our equation and we just have one variable. So we can just rearrange the equation for that one variable. So it looks like we have three things multiplying on the right and three things multiplying on the left. If we want to solve for C, then we would need to move this and this over. So we're just going to divide both sides by negative 71.3 and then this delta T.
Could you multiply all that together?
On this side?
Yeah.
Yes, you can do that.
Divide that by that.
Yeah, we can. Let's do that one. So why don't we just see, what is 26.7 minus 88 degrees Celsius? Okay. So we're gonna have negative 61.3 times 71.3, or negative 71.3 times C on the left side. And the right side is just everything. So what would those two multiply to? 1,000 or 4,000? Okay. 4,370.19 C. And that equals, let's just go ahead and multiply the right side out. And one thing to be really careful about in this chapter is you need to, like, since we're dealing with C's and degrees Celsius, you have to put the degree symbol, because otherwise it looks like this is the temperature and things get really confusing. So just pay super attention to your units. So we're going to the right side?
Yeah.
1,977.033. And it looks like the unit would be here. Because grams cancel with 50, substitute cancel with 50. And this one would be grams degrees Celsius. In fact, we're not moving grams degrees Celsius. So now we just have to solve for C, which means we need to divide both sides by this number, 4,370. So we're going to do that. And then I'll write it all back in and tell you what to do. Since it's a specific heat of the metal, it should be less than 1. I would say probably less than 0.5. Okay. 4, 5, 6, 7. And it looks like our units are correct. We had joules on the slide and divided it by grams degrees Celsius. And the units for specific heat are joules per gram degrees Celsius. So now we just have to figure out how many liquids we have to do. It's important to note that we did addition and subtraction before the multiplication. So whenever we subtracted these numbers, we still got only 3 liquids. So like if it was just 1.3, then we would have had 2 liquids in the final. You always have to look at the addition first. So like this one would have ended up being a 2 liquids, right? Would have been 3.7. So I would say with all the multiplication going on, this is 3 to 3, this is 3 to 3, 3, 4, this one would be 2 after the subtraction. So I would say this is around our finalized 2 liquids. So it should be 0.46 to the stuff. So is that what you already got?
Okay, so for 4370 plus 6 times grams per day Celsius, what do these grams cancel out? Because that, like when we're doing the which figures at the top, the grams cancel out, so 129 grams and what's that grams cancel out?
Yeah, so if we're just looking at the units, on the right side we have grams times joules per gram degrees Celsius times degrees Celsius. On the left side we have grams times, I'm just going to say X, because I didn't really have units, times degrees Celsius. But yes, on the right side, grams and grams cancel. And on the right side, degrees Celsius and degrees Celsius cancel. So on the right side, we had joules, which ended up being the top of this fraction. On the left side, we had grams degrees Celsius. And since we divided this over, it ended up being joules on top, grams on bottom, and degrees Celsius on the bottom. So you are right, it did cancel on the right side, but on the left side it didn't, and that's why it ended up on the bottom.
Oh, okay. Thank you.
Yeah, so that was actually the part I did first. Now we can go back and do the first part. We all did this with. So for the first part, since we know that this top equation that I have written up here, the Q or the negative Q of the metal is equal to the Q of the water. Well, now that we know what the specific Q of the metal is, we could just do the metal. But at the beginning, we didn't know what the specific Q is of the metal, so I would say we would have to find how much heat the water is going to need. So that's how you do the first part. What was it asking exactly? Well, for the first part. Okay, so the metal gave up with the negative NC delta Q of the metal, but since we didn't know the specific Q of the metal at the beginning, we could just find how much the water absorbed, because the amount of heat the metal gave off is the same number as the amount that the water absorbed. So we're just going to do Q of water equals NC delta Q of water. And, yeah. So we just need to know what the mass is, the 60 and the delta Q of water. So there are 129 grams of water, and I think it was 3.7 for delta T from the last question. So if we have 129 grams of water, we know that the specific heat is 4.184 joules per gram Celsius. And then we know that the delta Q was 1.0 Celsius. So Q is joules, which is what we're trying to find, and how to keep the metal give off. So we're just going to have a multiplication problem, essentially. Okay.
I think 1,997.0.
So it looks like it's going to have two secrets in this subtraction. So what was it, 1997?
Yes, 0.023.
Okay, 1997. So if we want two sig-figs, that means we're gonna keep the 1. The 9 is going to round up to a 10.
Mm-hmm.
So it's going to be 2,000 joules. But in WebAssign, you can't do the little bar thing, so we need to put it in scientific to show that it's not 1 sig-fig, it's 2 sig-fig. So it would be 2.0. Joules. Yeah, that's fine. Okay.
Could you explain the sig figs again for 1,997? How do you do that again for the 2 sig figs?
The rounding or where the 2 came from?
I think it's like the rounding.
Okay. So we wanted to, whenever I keep 2 sig-figs, like if I know I'm rounding to 2, I always write the first one. So it would be 1. and then I would round the second one. So if we look at the 9, the number after it is greater than 5, which tells us that the 9 is going to round up to 10, but you can't put a 10 in that place, because you put a 10 there, now it's a 1 and a 0. So when the 9 rounds up to a 10, it just turns into a 0, and then it rounds the 1 up to a 2. So that's where the 2, 0, and then everything after this 0 is non-significant, so you just write 0. So really these two were the only significant ones, which is why we had to put in scientific, because otherwise that's just one secret. Okay. Does anyone any questions online? Nope. Okay, well, this was the Chemistry 1045 workshop. I have one of these every week at the same time, so feel free to come in if you have any questions. And that's it. See you next week.